So we're looking at taking the derivative of exponential functions. So let's start with taking the derivative of e to the x, and let's derive that derivative. And so remember, when we take the derivative, we have y is equal to f of x, then the derivative of f of x, or dy dx is another way to write this, is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So that was the formal definition. And so we're going to go in and use the formal definition on y equals e to the x. And so if we do that, it would have this is equal to the limit as h goes to 0. And wherever we see an x in our function, we're going to plug in x plus h. And so doing that, we have this is e all raised to the x plus h power minus our f of x function, which is e to the x, all over h. We're going to use rules of exponents to rewrite this. And so recall, rules of exponents said if you had the same base, like b to the m times b to the n, this was the same thing as taking the same base b and adding those exponents, b to the m plus n power. So we're going to go in the opposite direction because we have this e raised to the x plus h power. And so we can rewrite that. Let's bring down the limit. We can rewrite e to the x plus h as e to the x all times e to the h minus e to the x all over h. And so notice here in the numerator, both terms have this e to the x function. And so we can factor that out. So let's factor out e to the x from the numerator. If I factor out e to the x in the numerator, I'm left with this e to the h minus 1 all over h. And we need to bring down our limit because we haven't taken it yet. Our limit is as h goes to 0. So if there's any other variables in there that's not h, and e is not a variable, it's a number, 2.718, it goes on forever, we can pull it out. And so this e to the x is not being affected as h goes to 0. So we can technically bring this out in front of our derivative or limit. So this is the same thing as e to the x times the limit as h goes to 0 of e to the h minus 1 all over h. The problem is if we do direct substitution now, and we go in there and we plug in 0 wherever we see an h, we would get this e to the x all times e raised to the 0 power minus 1 all over 0. Well, e to the 0 is 1. And in the numerator, then we have 1 minus 1, which is a 0. And so we're getting an indeterminate form, this 0 over 0. So really, that limit didn't tell us anything. And so we can go in here and start manipulating it. Or, and we really don't know how to do that yet in this case. But we can also use rules that we had done before. So basically what we're doing, right, as a limit, let's just look at this piece, as h goes to 0 of e to the x, not e to the x, e to the h minus 1 all over h. And so we want to see what's happening as h gets closer and closer to 0. So we want to see what's happening as we're coming in to 0 on the left of it. So how about negative 0.1, negative 0.01. So we want to see what's happening as we're coming into the left of 0, and we want to look at it as we're coming into the right of 0. So how about on the right of 0? So bigger numbers bigger than 0, but close to 0. So positive 0.1, 0.01. And let's see if that's going towards any particular number or not. We know if those are going to both of the same number, y value, then the derivative or the limit exists, and that's what the limit is. So we had pulled up on Desmos this function, e to the h minus 1 all over h, and we're going to start plugging in numbers and get back what that y value would be. Just pulling it in here. And so I'm looking at, I want to know when h is negative 0.1. So I would say I want to evaluate this at f of negative 0.1. And so if I do that, I get 0.9516. Let's look at as we get closer, negative 0.01. Notice I'm getting 0.995. So to me, it looks like it's approaching 1, but let's look at a little bit more. So how about 0.0001? And it gets 0.99995. So it's looking like it's approaching 1. So let's do the same thing on the right. So f of 0.1, we get 1.05. But as we get closer to 1 on the right, 0.01, 1.005. So how about 0.0000001? And notice that this is 1 point and it has lots of zeros and then 49. So I can tell by looking at this as we are approaching on the left and the right, the y value that we're getting closer and closer to is 1. And so we're going to say that our limit as h approaches 0 of e to the h minus 1 is 1. Okay, so we're going to have to rewrite this. So this is equal to the limit. Actually, let's pull the e to the x out front. E to the x times the limit is h goes to 0 of e to the h minus 1 all over h. Well, we just said that that limit was 1. And so we have this is equal to e to the x all times 1, which is e to the x. So we just derived that the derivative of e to the x is itself e to the x. So if f of x equals e to the x, f prime of x, the derivative is equal to e to the x. Let me pause and see if you guys have any questions. So now let's look at f of x equals e raised to g of x. So g of x could be x, or it could be some function in terms of x. X is y equals x is a function in terms of x. That's why I said it could just be x. But if we wanted to find the derivative of this, notice this is a composition of two functions. And we can think of our outer function, and maybe we should actually, before we do that. So let's say we had some function h of x, and it was in terms of a composition of two functions, f of g of x. If we took the derivative, h prime of x, this was the derivative of our outer function. So this was equal to the derivative of the outer function, f prime, of the inner function. So the inner function stays the same, of g of x, times the derivative of g of x, times the derivative of the inner function. So let's, and this was the chain rule. So let's go back to e to the g of x and let's figure out what is our inner function and what is our outer function. So in our case here, the outer function. So let it be y equals e to the u, where our u value, if we plugged it in wherever we saw a u, we want that to be g of x. So u equals g of x. Another way for this chain rule of writing this, we could say that dy dx is the same thing as taking the derivative of y with respect to u. So dy du times du dx. So if I'm looking at it that way, and I want to find the derivative of e to the u, so dy du, well, we just found that the derivative of e to the x is just e to the x. So the derivative with respect to u of e to the u is e to the u. And we want to find the derivative of u, so with respect to x. So du dx, well, I don't know what g of x is, but I know I can write that g of x as g prime of x. And so if we go in here and we use this formula, dy dx, this is equal to dy du, which we just found to be e to the u, times du dx, which we just found to be g prime of x. The only thing is that we want this derivative all in terms of x and not have the variable u and x in it. And so we have to go in here and we need to figure out what u was. Well, we chose u to be g to the x. And so the derivative of f of x, which is e raised to the gx, so f prime of x is equal to, I can write as dy of dx, which is equal to e raised to the u, but u was g of x, times the derivative of g of x. So we got a new rule. If y equals e raised to the g of x power, the derivative of that function, dy dx, I usually put the derivative of my exponent down first. It's the same thing though. So I usually write g prime of x times the original function, e of g of x. So that was the rule that you really need to know. And notice if we were using this rule right here on just e raised to the x power, we would get the same thing, e to the x. So if we use this rule, and I just said, use this rule to find f of x is equal to e to the x, find f prime of x. Using this rule. Well, it says we're going to take the derivative of our exponent. Well, if I look at my exponent, the derivative of x is just 1. So the derivative of my exponent, and then maybe I could just write it like that first. I'm going to take d dx of x times the original function that we're starting with. Our original function we started with is e to the x. So the derivative of x is just 1 e to the x, which is e to the x. which we already showed that that's what we were going to get. So if you have a derivative, base is e of some exponential function, you're going to take the derivative of the exponent times the original e. And that is our rule for that piece. Okay, so let's look at some examples where we're taking derivatives with functions that have e in there. And so we want to find the derivative of -5 times e raised to the 4x squared. And so if we use that rule, and I was just saying, well, that -5 is the coefficient in front, so that's just going to stay there. And then we're going to take the derivative of our exponent. So d, I'm not going to do it yet, d dx of 4x squared times the original function itself of that e. 5 is out here, -5 is out here. So the original function itself is just e raised to the 4x squared. So this is equal to -5. So derivative of 4x squared. So bring our power down front and multiply it to that 4. So 2 times 4 is 8. X, subtract 1 from our power, times e to the 4x squared. So clean it up a little bit, -5 times 8. So this is -40x e to the 4x squared. So let's look at another one. What if it was y is equal to parentheses 3x cubed minus 4x end your parentheses, and this is raised to the e to the -5x power. And again, we want to find the derivative of this. So I notice a couple of things. I noticed that I could distribute that e to the -5x, but if I distribute it, then notice I'm going to have to use the product rule when for the first piece minus the product rule for the second piece. Where if I just left it like this without distributing it, I'd only have to use the product rule once. So let's treat the parentheses as one function and the e as another function. And so we're going to need to use the product rule. And the product rule, recall, was take the derivative of the first function times the second. So let's just write that. So this is y is equal to the derivative of the first. So d dx, not taking the derivative yet, 3x cubed minus 4x times the second, which is e to the -5x, plus the first function, which is 3x cubed minus 4x, times the derivative of the second function. And our second function in here is this e to the -5x. So times the derivative d dx of e to the -5x. Okay, so let's go in, take the derivative of the piece that we need. So the derivative, well, taking the derivative of 3x cubed minus 4x isn't too bad, right? So bring our power down front, 3 times 3, that gives us 9x, subtract 1 from our power. So 2. Derivative of minus 4x is just minus 4 times e to the -5x plus the first, so 3x cubed minus 4x. Okay, so the derivative of the e function, we're taking the derivative of our exponent. So the derivative of -5x, which is -5, times the original function itself, which is e to the -5x. Okay, so looking at this, I notice I can pull what they have in common out front. Notice that we have this e to the negative 5x in here for this first grouping. And we have this e to the negative 5x over here with this second grouping. So if we pull out that e to the negative 5x piece, you would just be left with, for that first grouping, the 9x squared minus 4. If we pulled it out of the second piece, we're going to have this left. So we'll have this plus parentheses 3x cubed minus 4x times this negative 5 bracket. I see that I did an error here. I did not write this was the derivatives. This was dy dx. dy dx. So let's clean up what's inside the bracket a little bit. We can distribute our negative 5 into that parentheses. And then if we have any like terms, which doesn't look like we do, we would combine those. So our derivative is e to the negative 5x. So this is going to give me negative 15x cubed. I kind of want to do it in descending order of powers, if that's okay. So let's write that first. So negative 15x cubed. Negative 5 times negative 4x. That's going to be a plus 20x. So let's just write down the plus 9x squared next, plus our 20x. And then we have this constant minus 4. So we found that derivative, and we wrote it in a way that later on, when we need to find out when our function is equal to 0, we have it now factored somewhat, so we could set each factor equal to 0 and try to solve from there. So we have y is equal to e to the x all over 2x plus 1, and we want to find the derivative of that. So I noticed that we have a quotient. We need to use that quotient rule. There's no way, I guess I could manipulate it a little bit. If we wanted to and didn't want to use the quotient rule, we could rewrite this as y is equal to e to the x. Well, if I don't want this denominator here, I could bring up the whole denominator. So put it in parentheses, 2x plus 1, and that would change the sign of the exponent of that parentheses to a negative 1. So we could, if we wanted to, rewrite this and use the product rule. So we could keep it as a quotient, use the quotient rule, or rewrite it as a product and use the product rule. And I notice within that product rule, when we take the derivative of this 2x plus 1 raised to the negative 1 power, I'm going to have to use that chain rule. But just so that we have, we just did one with product. Let's look at it using the quotient rule. So let's just write out what we are doing for the quotient rule. So the quotient rule says take the derivative of our numerator. So d dx of our numerator, e to the x, times our denominator. So our denominator is 2x plus 1, minus our numerator, e to the x, times the derivative of the denominator. So d dx of 2x plus 1, all over the denominator, which is 2x plus 1, that quantity is squared. So going through here, the derivative of the e to the x, my power is just x. So derivative of e to the x is just e to the x itself, all times this 2x plus 1, minus this e to the x. And so the derivative of 2x plus 1, well, derivative of 2x is just 2, derivative of 1 is 0, all over 2x plus 1 quantity squared. So notice that in the numerator, each of those groupings have e to the x in common. So we can technically pull that e to the x out of both of those pieces. And if we do that, we would be left with 2x plus 1 minus, pulling e to the x out over here, we would be left with just a 2 all over 2x plus 1 quantity squared. So let's just combine like terms in that parentheses in the numerator. We have 2x and we have plus 1 minus 2. So that would give me a -1. So 2x minus 1 all over 2x plus 1 quantity squared. Okay, so there was a great question about our denominator, how we have, with the quotient rule, we're squaring the denominator. I noticed that I did not distribute out 2x plus 1 times 2x plus 1. That just is going to make things a little more complicated in the future when we are going through and we're going to be trying to find out when is our derivative equal to 0 or where it's undefined. And so right now I wrote it out really easily because I factored the numerator so I can see when is my numerator equal to 0. I would set each factor equal to 0. And functions are undefined on values which set our denominator equals 0. So without expanding that square, it's making it easier that we could set that equal to 0 and find.